Today I want to look at two very different problems from the 2023 Bangladesh Math Olympiad. So the first one is a nice integration type problem, and the second one is maybe what I'll call an exponential factorial Diophantine equation. Okay, so let's jump right into the first one. So let's suppose f is a real valued function on the real numbers that is integrable, and it has the condition that if a and b are real numbers that multiply to 1, then a times f of a plus b times f of b equals 0. And then our goal is to find the integral from 0 to infinity of f of x dx. Okay, so let's see how this goes. So let's maybe take any positive real number. So I'll say that that's a real number on the interval from 0 to infinity. And then let's note that if we take x times 1 over x, we simply get the number 1. And now I want to look at this blue boxed condition over here where a is equal to x and then b is equal to 1 over x. So I'll write that here. So we've got a is equal to x and then b is equal to 1 over x inside of our given condition means that x times f of x plus 1 over x times f of 1 over x is equal to 0. Okay, so let's maybe underline that for now, and then observe that we've got this 1 over x composed within the function f. And that really motivates us to do some sort of change of variables on our integral to see if we can write it, in a slightly different form. Okay, so what would that change of variables be? Well, we're clearly trying to get a reciprocal within the function. So let's maybe set x equal to 1 over t. That makes dx equal to minus dt over t squared by taking derivatives. And then if x is equal to 0, well, I'm going to write 0 plus because it's coming from above given our bounds of integration. That means that t will be positive infinity. And then likewise, if x is equal to positive infinity, then that means that t is 0 from above. Okay, so that's how the bounds of integration are going to change. Okay, so now let's apply that to our integral. So that means we've got the integral from 0 to infinity of f of x dx is negative the integral from infinity to 0 of 1 over t squared times f of 1 over t dt. So that's just applying this substitution. Okay, but let's notice that that minus sign out front can switch the bounds of integration, and then simultaneously I'll do a trivial change of variables back to x. That'll give me the integral from 0 to infinity of 1 over x squared times f of 1 over x dx. Oh, but let's compare that with our green underlined equation and observe that we can easily solve for 1 over x squared times f of 1 over x inside of this green underlined equation. And that'll look like 1 over x squared times f of 1 over x equals negative f of x. Okay, so let's maybe put a box around that. Okay, well, let's see if we can put this all together into a nice, one-line calculation. And we're going to use this yellow underlined identity to help us. So let's start over here. We've got our integral from 0 to infinity of f of x dx. So that's our goal. Now I'm going to do this trick that I like to do, which, albeit is a little bit silly, but I just like how it condenses everything down into one line. So I'm going to write this as 1/2 times the integral from 0 to infinity of f of x dx plus the integral from 0 to infinity of f of x. Well, that's just 1/2 times something plus itself. Okay, but now I'm going to use this yellow underline to rewrite the second integral. So I've got 1/2, and then I've got my integral from 0 to infinity of f of x dx. I'm not changing the first integral. And then plus the integral from 0 to infinity of 1 over x squared times f of 1 over x dx. Great. But next up, I'm going to use this green box to rewrite the second integral. So that's going to leave me with 1/2. I'm not rewriting my first integral, so I've got that integral from 0 to infinity of f of x dx. But then that green box allows us to write that second integral as, well, negative that first integral. So I have minus the integral from 0 to infinity of f of x dx. But now those two cancel, giving us 0. So now reading this from the extreme left to the extreme right, we have found our goal value. The value of that integral is 0. Okay, now let's move on to the second problem. Okay, for our next problem, we're going to find all non-negative integers a, b, and c, so that a factorial plus 2 to the b is equal to c factorial. Okay, so now the first thing I'm going to do is rearrange this equation a little bit. We'll write 2 to the b is equal to c factorial minus a factorial. Great. And now let's make our first little observation that's going to help us. And that is 2 to the power b is bigger than or equal to 1. That's because b is bigger than or equal to 0, and, well, exponential function has that property. Oh, but if this left-hand side is always bigger than or equal to 1, that means the right-hand side is also always bigger than or equal to 1. But what that tells us is that c has to be strictly bigger than a. Otherwise, the right-hand side would not be bigger than or equal to 1. Okay, nice. And now let's move on to maybe our second observation. And that is if a and c are both bigger than or equal to 3, then that means that c factorial minus a factorial is a multiple of 3. Oh, but that means that 2 to the b is a multiple of 3. But then, well, really by the fundamental theorem of arithmetic, we know that a power of 2 can never be a multiple of 3. So that gives us a contradiction here. So in other words, we cannot have this setup where a and c are both bigger than or equal to 3. Okay, so now let's do a little bit of casework. Okay, so our first case will be the case if c is bigger than or equal to 3, and then a is less than 3. So let's just notice that we could have c bigger than or equal to 3 and a less than 3, but we cannot have the opposite because of our inequality up here that c is bigger than a. But now let's observe that if a is less than 3, then that means that a is equal to 0, 1, or 2. Okay, so now let's cover each of those on their own. So, well, what happens if a is equal to 0 or 1? Well, that means that a factorial is equal to 1. That's because 1 factorial is 1 and 0 factorial is also 1. But then that gives us the equation 2 to the b is equal to c factorial minus 1. But notice that that is going to be strictly bigger than 3 factorial minus 1, which is strictly bigger than 5. But now let's notice since c is bigger than or equal to 3, that tells us that c factorial is even. Oh, but that means that c factorial minus 1 is odd. So let's see what's happened here. We have 2 to the b is bigger than 5 and 2 to the b is odd. But 2 to the b only takes on a single odd number, and that is the number 1 when b is equal to 0, but 1 is not bigger than 5. So that leads us to an impossibility as well. So that means we cannot have the possibility that A is 0 or A is 1, leaving us with one last possibility in this first case, which is A is equal to 2. But let's give ourselves a little more room for this. Okay, so now we're looking at this case when A is equal to 2. But we're actually going to split this into a couple of subcases as well because there's an obvious solution that jumps out. And that is the case when C is equal to 3. So if A is 2 and C is 3, that means 2 to the B is equal to 3 factorial minus 2 factorial, which is 6 minus 2, which is 4. So that means we have 2 to the B is equal to 4, which means that B is equal to 2. But that gives us a solution. We've got A is equal to 2, B is equal to 2, and C is equal to 3. Okay, well, that's good news. We have at least one solution to our equation. And now let's maybe take this and move on to the maybe bigger case when C is strictly bigger than 3. Okay, but that tells us that C is bigger than or equal to 4. Okay, well, let's go from there. Now we'll write 2 to the B as C factorial minus 2 factorial, which is C factorial minus 2. Okay, but now notice that C factorial is a multiple of 4. So I'm going to write this as 4 times K minus 2. And then I'll just note here that C factorial is equal to 4 times K for some K bigger than or equal to, well, actually it has to be bigger than or equal to 6 because 4 factorial is equal to 24. But let's observe that we have B bigger than or equal to 2 here as well. And that's simply by the size of the right-hand side. So I'll note that here as well, that B is actually strictly bigger than 2. And again, that's because the right-hand side is actually pretty big here, given that C factorial is like 24 at least. 24 minus 2 is 22. So definitely B is bigger than 2 based off of just simple powers of 2. But since B is bigger than But since B is bigger than 2, what we can do here is divide both sides by 2. And that'll give us 2 to the B minus 1 is equal to 2 times K minus 1. But now let's observe that this left-hand side is most definitely even because B is bigger than 2, thus B minus 1 is bigger than 1. And this right-hand side is odd. But an odd number can definitely not be equal to an even number, so that means we have no solution down this line either. Okay, so that means if C is bigger than or equal to 3, we only arrive at this single solution here. Okay, now let's look at our next case. Okay, so we just looked at our case when C was bigger than or equal to 3, and we got this solution where A and B were 2 and C was 3. Now let's look at the case when C is less than 3. And recall that A always has to be less than C. And then, well, since C being less than 3 only gives us a couple of possibilities, we can check this just one at a time. So let's look at the case when C is equal to 2, which tells us that A could be equal to 0 or 1. But that means that A factorial is equal to 1. But that means we have 2 to the B is equal to 2 factorial minus 1. But 2 factorial is 2, so we have 2 minus 1, which is 1, which tells us that we have B is equal to 0, because 2 to the 0 is 1. Oh, but that gives us a solution. So we've got this solution where A is equal to 0 or 1, B is equal to 0, and C is equal to 2. Okay, so we've got another solution to go with the one that we've already found. Now let's move on to the next possibility. That next possibility is the case when C is equal to 1. But now if C is equal to 1, since A has to be smaller, that means that A is equal to 0. But that means that c factorial minus a factorial is 1 factorial minus 0 factorial, which is 0. But that's not possible because 2 to the b is always bigger than 0. So we don't get a solution there. And likewise, the case when c is equal to 0 is not possible because that doesn't leave us any possibility for a. So taking a step back and looking at what we have these exactly, well, it's really 3 solutions based off of the choice right here that we have for a. And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.